Good afternoon, ladies and gentlemen. My name is Stan Forrester. I'm a pre-algebra teacher at Southport Middle School. This is 24 August, and today was our first day. We had a little bit of trouble with the internet. Not everybody was able to see the materials we were doing. So I wanted to make sure to pre-record this stuff so that if there's a problem, you can go straight to YouTube or to a linked video and you can get this material. All right? So let's turn this camera around and take a look at our materials here. Okay, so square numbers. Okay, by the way, my name is Dr. Stanley Forster. We're doing this for Southport Middle School on 24 August 2020. Okay, these are the square numbers. That's what we're going to be working with today. And you're going to say to yourself, oh my goodness, what are we doing with square numbers? What is a square number? And, what does it have to do with anything that we're going to be doing? Well, you're going to find it's really, really applicable to the stuff we're going to do in Module 1, and when we get to the Pythagorean theorem, how can you make sure that, a corner is square, or, how do you build houses so they don't fall down? These are actually very, very applicable. Okay, so let's start off first with, here's some numbers. It's a sequence of numbers, and that's actually what they call it in math. It's a sequence of numbers. 1, 2, 3, 4, 5. And you can probably guess what these are already. Okay. Oh, what pattern do you see? And there's a little thing here that says the 3 dots at the end of the list. That means that the list continues in the same pattern. Okay. And I'm sure you pretty well figured this one out. These are the integers or counting numbers. Okay. You can have 1, 2, 3, 4, 5, 6, or something. Okay. You don't. You have 1 table, 2 table, 3 table, 4 table. You don't have 4.5 tables. You have 4 tables. And you have a pile of kindling on the floor, because if it's half a table, it's not really a table. It's just parts. Okay, you could have smaller tables. Okay, you could have half a share of a table, but a table itself, it's either a whole table or it's kindling. Okay. All right. What about 1, 3, 5, 7, 9, 11? I bet you've got this one too. And if you do, give yourself a pat on the back, because these are the odd numbers. These are odd numbers. We're going to skip. We're going to skip all the multiples of 2. We can think of this as like the integers, all except for the even one. So 1, there'd be a 2 in here, but we skipped it. 3, and then skip the 4, 5, skip the 6, 7, skip the 8. All right, and those are the odd numbers. Okay. Here's a fun one. Now, 1, 1, 2, 3, 5, 8, 13, 21, 34. Now this one's really odd. Actually, it's actually got a repeated number at the very beginning, 1 and 1. But you got to ask yourself, what could the relationship be between like 1, 1 and 2, or 1, 2 and 3, or 3, 2, 3 and 5. By the way, I'm giving you a hint here. Okay, 3, 5 and 8. I bet you've got it figured out already. Okay, if you take a look and you take these first 2 numbers, you can add them together and get the third. So for any number here, you take the 2 preceding ones and add them up, and that'll give you that number in that place here. Okay, so like 8 is 5 plus 3. 3 is 2 plus 1. 34 is 21 plus 13. Okay, and it just keeps on growing. And this is called the Fibonacci sequence. And you're going to get into science and chemistry, and you're going to hear this all over the place. And one of the reasons that we find it in nature is that nature tends to be very efficient. Okay, now can you imagine having to have a blueprint for an entire corn plant? That would be like, no, you don't need that. What you need is a principle. You need a principle. Like, for instance, where are you going to put the leaves on a corn plant? So we can imagine that we can see a corn stalk. We come around it 5 times, and after the 5th spiral coming up, we take a look, and there'll be 1 leaf right above the other one. Okay, so you don't have to have a plan for an entire corn plant. You just have to store the number 5 somewhere. And as a matter of fact, you don't even have to do that. You have to just have 1 and 1, and the principle of adding together, like 1, 2, 3, 4. Like you just add these numbers 4 times. If you have 1 and 1, you can get 5. Okay, so it's a very efficient way of storing information. Lots of other things, like, for instance, whole families of plants are classified by how many leaves how many petals are on their flowers, like 5, 8, 13. And we just see these numbers appearing again and again and again in nature because they're just very easy to store. Here's the one that I actually wanted you to look at. Okay, so we have this sequence. We can see that it increases just like the other one did, like that Fibonacci sequence and all the others. We have this continued pattern here. And let's see if you can figure out what that pattern is. I'm going to give you a hint. I'm going to take 1 and I'm going to put 1 dot down. And I'm going to take the next in the sequence and I'm going to put 4 dots down. And then 9 dots. I'm pretty sure most of you have gotten a piece of graph paper and played games with something like this. There's little square arrays here. But you can see 16, that's 16 is a square array too. I wonder if you're going to be able to take 25 and make that a square array as well. Indeed you can. And that's exactly what we have. These are the square numbers. Okay? And we can look at our multiplication table. We can see that 1 times 1 is 1, 2 times 2 is 4. See that 4? Okay? 25. 5 times 5 is 25. That's the diagonal, right down the center of your multiplication table. Okay? Are there any other patterns we can see? I mean, just because we found one pattern doesn't mean there aren't any others. Let's take a look at, I'm going to throw a 0 in there so I can do this first one. Okay, so we take 0, or 1 minus 0. 1 minus 0, that's 1. And then 4 minus 1. 4 minus 1, that's 3. 9 minus 4, that's 5. Oh, wait a minute, look at that. All of our odd numbers showed up again. Kind of so, you know, you have the square numbers and you have the odd numbers hidden in there somewhere. You know, that's kind of cool, isn't it? Okay. Also, what about the difference of 2 adjacent perfect squares? That's always going to be odd. Okay. But what about if you skip one, every other one, like 36 minus 16? Is that odd or even? And how does that work? Does it work for any 2 pairs if you just skip one, like 100 minus 64? Is that odd or even? What about 3? What if you skip 3? I wonder if this could be, you can play around with that if you want. Okay. Okay, we're going to, in the next module, we're going to need to work with square roots. Now, so these perfect squares have integer square roots. You know, those counting numbers that we talked about. So the square root of 36. That's this radical sign here. That's what we say. We're going to ask ourselves, what times what equals 36 when we put that radical there? And it turns out that it's 6, or plus 6 or minus 6, okay? But we usually talk about what we call something called the principal root, so it would be the positive number. So positive 6 is the square root of 36, okay? And these are the only, perfect squares are the only ones that have these integer square roots. If we just move a little bit away from 36 to 37, we take the square root of 37, we get, so what we could estimate that, like square root of 36 is 6, so square root of 37 is going to be a little bit more than that. But it turns out the square root of 37 is 6.08276, and it just keeps on going forever. And these are irrational numbers. All right, and we can get, there's a great story about this, about Greek philosophers who discovered the secrets of the universe, and then there's some guy who comes up and says, nah, ain't that way. They got these things called irrational numbers. And so they picked him up and threw him off a cliff. And that's not a metaphor. They actually did throw him off a cliff. So, yeah, so, you know, mathematics may not be as, you know, it could be a little more dangerous than you thought. Okay, anyways. So, and it's also kind of a reason why we think about like irrational, and why we use the same word for irrational and crazy, like these numbers like this and crazy, because at one point it drove people a little crazy. And there's also a little story there about ratios, rational and ratios. Okay, so square root of perfect square is one kind of number. I'll give you a hint, it's called a rational number. Okay, and square root of non-perfect squares are treated differently. Okay, crazy. All right. Okay, it can also help you in memorizing your multiplication tables. Okay, remember they're just straight down here. Straight down the diagonal here. Okay, these perfect squares are 10% of the entries you need to have memorized. The adjacent ones, the ones adjacent to that diagonal, okay, we can also figure those out, like 8 times 7. 8 8 times 7, we could look that up, it's 56. But if you don't have a calculator handy, you just remember that 7 times 7 is 49. Okay, 7 times 7 is 49. And another 7. 7 times 7, or 7 squared, plus 7 is 56. Okay, so just right here, we have an array here that's 7 tall, 8 long, 7 times 8. Or we have 7 times 7 plus another group of 7. And that is indeed 56. Okay? Okay, if you already know you have your multiplication facts for 1 and 2, and then for 5 and 10, and maybe even another one for 9. If you don't have this one for 9, I'll show it to you in small group. Just ask me about it and I'll show it to you. Okay? Then we're going to fill in those adjacent ones. Okay? And I want you to, we're going to notice something here real quick. There's another pattern. Okay? So 3 times 8, that's 24, and, I'm sorry. 8 times 3 is 24, and 3 times 8 is 24. These are kind of mirror images of each other. And at this point, all you have is 7 of those things to memorize. Okay, so that's my plea for and motivation for you to memorize your square numbers. I'd really, really like to have you memorize your square numbers up through 20. Okay, but the ones you really need to work with are 1 through 100, or the first 10 square numbers. Okay, and then sometimes if you've got like 15 squared and 20 squared, you can work your way back and fill in the blanks. Okay, but okay, so that's enough, and I'm going to let you guys go, and we're going to start on with our next activity.